good to go. Okay guys, thanks for coming. This is the final workshop I'm hosting. So as I've reiterated multiple times, this was meant to be a 4-part workshop series. We went over quantum hardware, software, algorithms, and applications. And today's just a little bit of a bonus. So today's lecture isn't explicitly related to quantum computing, it's more related to quantum physics. And as you guys can tell from the title here, so it's starting points of quantum physics. So I mean starting points very literally. So it's like, where do you start for like learning, but also just like in general, where did humanity start? And it's kind of interesting, so there's a few different angles that humanity started to interact with quantum physics, and they've all kind of converged. So that's what we'll be discussing today. So starting off, we're going to do a review, then we're going to just talk about textbook definition of quantum physics. We're going to talk about revolutionary experiments. We're going to talk about wave-particle duality. We're going to talk about models of the atom, and then we're going to talk about a little bit of math as well. How do you kind of understand quantum math? All right, so kind of starting off with a bit of like algorithms, quantum information review. So what is a qubit? So as we're all familiar, a regular bit is either 0 or 1, where a qubit, which is what's used in a quantum computer, is in a superposition between 0 and 1, and there'd be some sort of probabilities associated with it being 0 or 1, and then when you measure that qubit, it would be forced to collapse to either 0 or 1. So that's what a qubit is. Hardware recap. So in our quantum hardware lecture, we talked about a few things. Does anyone recognize any of the things here on screen? Cameron?
Josephson junction.
Yeah. So do you want to explain what a Josephson junction is?
I think it's like the molecules are moving so fast, so it like passes through like non-material, and then that's like something like.
Yeah, that's pretty close to what it is. So what a Josephson junction is, it's a type of way to create a qubit. It uses superconductors to create a loop. And if you have a loop of superconductors, you would expect the electrons to just travel in it infinitely, which is what happens if you have a loop of superconductor. But what occurs in a Josephson junction is there's a little cut, so it's like a fully completed circular wire with a tiny cut. And according to regular physics, it would be impossible for current to move around it because it's cut, so like this circuit is broken, nothing can move through. But because the cut is sufficiently small, some electrons can actually quantum tunnel through that small gap, and it still allows you to create a measurable current going through, and that current is only there because of quantum physics. So that allows you to create a qubit using a superconductor. So that's what the Josephson junction is, and we talked about this a lot in the quantum hardware lecture. You guys are more than welcome to watch that video if you want to hear more about it. Just a few other things here too. So this is a laser-based quantum computer. This is Xanadu's computer. I've actually seen this in real life, or their old version. This is the Majorana 1 chip. It was a breakthrough quantum computing chip by Microsoft. It uses a different type of fundamental strategy. So just kind of showcasing here that there's a lot of different ways to make a quantum computer. I think we discussed maybe 9 in the quantum hardware lecture. Whenever you can try to tease out quantum phenomenon, you can theoretically try to make a quantum computer. And then top left here, this is called the quantum fridge. It basically allows these components to be cooled down to close to absolute zero, negative 273 degrees Celsius. And that's a huge challenge in quantum computing, is trying to keep everything cold enough to function properly. All right, just a few other big points. So there's 2 types of qubits. There's physical and logical qubits. So a physical qubit exists, as the name suggests, physically on the hardware. So for example, each Josephson junction could theoretically be 1 qubit, but it would probably be prone to noise, and there could be issues with only having that one physical qubit. So what we do is we take like up to 1,000 physical qubits, and we combine them in code, and basically take the average output to make a logical qubit. So right now, IBM, they have 1,000 physical qubits. Realistically, if they wanted to have an error-proof physical or logical qubit, they'd likely need to combine all 1,000. So what this kind of showcases here is, in order to have enough logical qubits to do useful things, we probably need millions of physical qubits. So that's the big thing to keep in mind. We're about 1 million times off where we need to be. Type uncertainty, so that's the discussion here. We don't know what type of quantum computer is going to succeed. If you do your PhD in laser quantum computers, and then there's a big breakthrough in superconducting qubits, then your knowledge might not be useful as the field progresses. Decoherence at scale. So this is the concept that as we add more qubits to a quantum computer, we start to see decoherence occur, which basically just means that there's a lot of noise in the measurements. So these are just the main challenges right now that's the hardware review. A little bit more about quantum information. So the reason that quantum computing is so powerful is because of these three concepts. We've gone over this multiple times. I hope that this slide is annoying because you've seen it so many times. So the first one is superposition. So as we saw when we talked about a qubit, it's in a superposition between 0 and 1. And that allows us to have like a very rich relationship with the data, superposition. Interference. So this is the idea. So since quantum can be represented as waves, which is something that we'll actually discuss today, you're able to interfere the waves. So when you interfere waves, they can either amplify and become larger, or they can collapse into just like a zero dead state there. So that's another important concept is interference. And then the last one here is entanglement, that particles can be connected, quantum objects can be connected, and that allows you to have huge states by only having a few qubits. And yeah, you guys can watch the quantum algorithms video if you want to learn more about this. We went over it in a lot more detail. Quantum software. So there's a lot of different coding languages that we can see up top. Pretty much every quantum computer has their own coding language, and since as we discussed a little bit earlier in the presentation, there's so many different types of quantum computers at the physics level. That's why they each require their own programming language. Some of the programming languages, like Google's CERT, are very low level, meaning that you're interacting with the quantum hardware very directly, whereas other languages like Qiskit are higher level, and it's actually built on top of Python, so you can do more general purpose programming. And one of the things we discussed about quantum software is it's very easy to make a quantum software project. It's harder to prove that it's actually better than just a regular classical computing. And that's like a big open question here is, what is actually useful to be coding with a quantum computer? And then talking about applications, this was the topic of last week's discussion, so we're just gonna go over two of the biggest ones today. First is optimization. So in a lot of optimization problems, like this occurs often in business, logistics, engineering, there's some problems can emerge. So the first one is cursive high dimensionality. So imagine that we're trying to optimize a warehouse. There's near infinite positions where you could place a box, where I could place the second box, a third box. There's this huge dimensionality, and that's one issue that classical computers have is as the dimensionality increases, they struggle to model it. The next one here is parallelism. So classical computers need to check each option individually, whereas a quantum computer can, in parallel, check all possibilities. The third thing is avoiding local minimums. So classical computers will often converge to a local solution, where quantum computers are able to reach the absolute best position. So optimization. The next thing here is chemistry. So this is something we'll discuss today as well. Real chemistry is based on quantum physics. So when we try to model chemistry using a classical computer, it's fundamentally challenging because it's not actually modeling the physics in its natural way. Whereas using a quantum computer, we're able to directly model the quantum activity. So it's much more efficient in that way. And the other thing to mention as well is we can use the optimization techniques talked about in the previous slide in chemistry. And then this is huge for drug discovery, advanced science research, material science, molecular engineering. All these fields are going to be majorly impacted by quantum computing. We also talked about last time two other applications. One of them was cybersecurity and how Shor's algorithm, which is a quantum computing algorithm, can break modern encryption. And we also talked about quantum AI, which is a larger topic. I was considering doing a whole workshop on that, but there's like some applications there as well. Okay, we also talked a bit about quantum business. I talked about how to be successful in quantum technology. I talked about two paths. Path A, graduate with a STEM undergrad, pursue higher level education, become an expert, and then become well positioned to get a career in quantum computing. This is more traditional. Path B would be start a career unrelated to quantum, monitor quantum developments closely, focus on quantum integration skills. Unless you go to your PhD, you're not going to be able to build the next quantum computer, but it might be somewhat simple, especially coming from maybe engineering business background, for someone like us to understand how to do quantum integration. And then start a business or join quantum integration business. So these are just something that we discussed last time, how to become successful. Moving on, one more point about quantum business is, let's just take a look at Xanadu. So Xanadu, right now they're valued at $3.6 billion, but their revenue is under $10 million, and they're not profitable at all. They have minimal clients. They have a very fancy laser-based quantum computer. What I'm just kind of showcase here is, that's a lot of money, $3.6 billion for a company that in terms of the financials is not justifying that valuation at all. So I'm just showing off here that people are making money even if the computers don't work. There's a lot of hype around quantum computing. So yeah, it's a bit strange, and quantum computing has really gotten mixed in with the AI hype. I was looking at some statistics, and I saw a statistic that it was like quantum and AI are going to save billions of dollars in the finance industry. But it's funny to me how they mix the words quantum and AI, because the reality is maybe they can prove that AI will save billions, but they just throw the word quantum in there just because they are, maybe they're invested in Xanadu or something. So there's a little bit of sneakiness happening in the finance. So now we're going to move on to the starting points of quantum physics. So I'd say the most natural thing to do if you're trying to learn about a subject is to search it up on Google, see what comes up. Just the definition that Google gave me, so I'm just going to read it out to you guys. So it says quantum physics, or quantum mechanics, is the branch of science that studies the behavior of matter and energy at the atomic and subatomic levels. It describes the universe on the smallest scales, where particles exhibit wave-particle duality, exist in superposition, and follow probabilistic laws rather than deterministic rules of classical physics. Okay, so it's a bit of an earful there, guys, but I'd say the one sentence definition is quantum physics studies the very smallest scale of things, and as we'll discuss in this presentation, a lot of things can't be divided further. Like if you take a knife, you could cut this table in half, and cut that in half, and cut that in half, and cut that in half, but eventually you reach the Planck length, which is like the quanta, which means smallest dividable thing of length. So the quantum physics studies the smallest dividable amounts of things. Moving on, so as I just kind of mentioned, so the quantum physics is named after the word quanta. A quantum, plural quanta, is the smallest possible discrete unit or packet of any physical property. That's kind of the main thing you mentioned there. So it's the smallest possible discrete unit is a quantum. So there's a lot of things can be quantized. So light can be quantized into a photon, matter into an atom, electric charge quantized by the electron. There's also the Planck length, which is the smallest length in the universe, and a lot of other things as well. These are just a few examples, but because I remember as a child, I would sometimes imagine, like, what if I kept cutting it? Like, how small would it get? Well, it turns out that there is a limit. So it's quite fascinating, and that's what quanta is. That's these things, and that's what quantum physics is named after. So if there's one takeaway from this presentation, it's the name quantum physics. If someone asks you what is quantum physics, you can say, well, quantum physics is a study of the quanta of things, right? So it's a little bit open-ended, and that's kind of one of the reasons why there's so many different starting points to it, because you could start with that light, you could start matter, you could start Planck length, you could start electric charges. It's quite a broad concept. Okay, so we're going to move on here to wave-particle duality. So this is one of the core starting points of quantum physics, and if you've taken high school physics, or at least in Alberta, they introduce quantum physics, and they do so through the wave-particle duality. So this is an experiment known as the double-slit experiment, which was performed for the first time by Thomas Young, who was a physicist in the early 19th century, and he's very famous because not only did he do this experiment, but he also learned how to read the Egyptian hieroglyphs. He's an Egyptologist, and to me that's really interesting because it took someone with a very advanced physics mind to decode the Rosetta Stone, which allowed the translation to occur between ancient Egyptian language and other more known languages. So anyway, moving on here. So let's say that we have, I have my own version of this, but let's say that we have this panel here, and it has two holes, two slits. And we shine the light through these two slits. This is what you'd think would happen. It would create two bars of light, right guys? That's what you'd think would happen. Does that make sense to everyone? That's what you'd expect to happen? And I don't want to spoil my own demonstration, but what actually happens is, since light is also a wave, we hit these two bars. So we hit these two bars, but then each of those two bars is almost like creates a ripple, as if you're on a lake, and those ripple creates waves. And some of those waves cancel, so there's no light, and other waves collide, so there's an amplified light. So that's what actually happens. And this experiment in 1802 by Thomas Young proved that light behaves like a wave. It has wave-like behaviors. So I've actually made one myself with the help of Alex here. It's a little bit finicky. And the further back I stand, the better. Let's see. Get this going. So look at the wall, guys. Oh, man. You guys see, like, it's kind of a bit transient, but you see how there's areas where there's a lot of light, and then areas where it's dark, going out to the sides. You guys see that?
Yeah.
So it's a little bit tricky to hold. But you guys can see on my demonstration where those like high spots are occurring and where the dead spots are occurring, and that's occurring because of the wave nature of light. One other comment as well, so this is 1802 when this was first discovered, and back then that was before you could buy lasers on Amazon one-day shipping. So what he actually did is he basically had a wooden box that was like a wooden cube and like a little hole cut out for someone's head, so you could stick your head in the box, and then the other side of the box there was like 2 different cuts so the sunlight could hit it, and then inside the box you could see like the lines from the sun. So pretty cool. 1802 that was discovered, and that proved that light had wave-like properties. That kind of brings us to the wave-particle duality. So the double-slit experiment by Thomas Young shows that light has wave-like particles. But other experiments, I'm not going to get too much into the physics of all the experiments we're talking about today. These are kind of meant to be starting points. So if you guys want to look into it yourself, feel free. But there's another set of experiments that show the photoelectric effect. Essentially what the photoelectric effect is light will hit an atom, like some sort of matter on this plate, and then it will eject an electron from that. And it turns out that only very specific energy levels of light can actually knock off those electrons. And since those are very specific energy amounts, it means that light had to be like a particle, like a collision ball hitting those electrons. And this kind of demonstrates, as shown here by these dots, those are photons, which are particles of light. That demonstrates that light also has this particle-like nature. So that's kind of a big starting point, is the wave-particle duality. Yeah, that's a core starting point in quantum physics. And also to mention as well, we can compare this to quantum computing and qubits, because when we have an unmeasured qubit, it's in a probability space. It's kind of like the wave. But then when we measure it, it becomes a particle, it becomes measurable, it becomes 0 or 1. So this also connects directly to qubits. Moving on here, I'm just going to talk about a few other revolutionary experiments. So this one here is Aspect-Bell's experiment. So this experiment, I was reading a little bit about it. I'm not fully familiar with all the physics involved, but it showed improved entanglement. And basically what happened is they have an atom here, and they make this atom emit 2 photons in opposite directions. So since they're emitting from the same source, they're naturally entangled. They have the property of entanglement. And essentially what's happening here is as they measure the polarity of one of these photons, the other one responds. They can manipulate that, and that proved entanglement. And that's a core experiment in quantum physics that proved without a doubt that entanglement was real. And what's interesting is Albert Einstein, he had his grievances with quantum physics. He has a famous quote where he says, "God does not play dice," referring to the fact that in quantum physics there's a high degree of randomization. But this experiment and others proved Einstein wrong, that quantum physics was real in the sense that randomization was occurring, and this proved entanglement. Just something to look into if you want to study why entanglement was possible. Okay, another experiment here. So this shows that matter itself is a wave. So we all know matter is a particle because it's right there, right? It's a particle. But it's also a wave, and they actually showed it very similar to the double slit experiment. So they shot electrons, which of course electrons are a type of matter, and they shot it through an atom, and it was basically the same as shooting the photons through the double slits. And then this image is kind of just AI generated, but it created the same wave pattern that you would see in the double slit experiment, but using matter. So it proved that matter is a wave as well. Pretty interesting experiment. Moving forward here, so this is another big starting point in quantum physics, and this is actually a starting point in quantum physics for humanity. And I'll talk about that in a moment here. So this is an experiment called the hot oven experiment or something like that. Anyway, this is related to the concept of black body radiation, which in itself is a significant topic. The idea is that when light hits an object, one of 2 things will happen. Either it will be reflected back, or it will be absorbed, and then it will be re-emitted. So those are the 2 different things that happen when light hits an object. So in this experiment, we have light going in, and we're like, heating up this object, we're giving it energy, and then we're measuring what kind of energy comes out. And what's interesting is you would expect that, some of us, if you've taken like some physics classes, you would have learned that light or electromagnetic radiation, which is the same as light, exists on a very wide spectrum. And according to classical physics, you would assume that the light that's re-emitted would be like equal throughout the whole spectrum. Or at least somehow like you'd see light from the whole spectrum come out. That's what you would expect to happen. But because of quantum physics, we see some weird behavior emerging where if the object that's re-emitting light is at room temperature, we'll only see like certain colors. Whereas if it's really hot, kind of like if you have like a really hot fire, that's when you start to see white and those other colors come out. So we kind of see that only when objects are at a very high energy will they emit those photons that are corresponding to the higher energies on the electromagnetic radiation, which just kind of proves that not all the light is coming out. So it's a little bit involved, and I could spend a lot longer personally myself learning about this as well, explaining, but this is a very important starting point. And there was individual Max Planck, and he took the results from these experiments, and he developed this equation. So E is energy, and then F is frequency. So as we know in the electromagnetic spectrum, different light energies, or like different spots on this have different frequencies. So his equation essentially connects the energy to the frequency of light, and it based on this constant he made H. And this was a very important moment for quantum physics and humanity. This is around the year 1900. He kind of creates this mathematical relation here, and it really opens up the box for humanity to start exploring quantum physics. So this is an important experiment and concept to look into if you want to learn more about how humanity started learning about quantum physics. So now we'll move on. So if you study quantum physics at the university level, you'll be working very directly with wave equations. So this is a very simple wave equation here. So this is like phi, or psi, that's just a symbol of x. X is just position. And then it's equal to some function here. So a very simple version would just be, even though there's some other constants, this is really just a sine of x problem. Those are the only, x is the only variable, and then just sine. So that would look something like this. We're all familiar with math, just like a basic sine function. So this, theoretically, a basic sine function could be your psi. So whenever you're looking at some weird quantum physics equation like this, just know that this equation, the psi of t, could theoretically be something as simple as a basic sine equation. So where I'm getting at here is just to talk about how, in reality, if you were to start doing quantum physics, especially at the mathematical level, you'll be needing to interact with wave equations. So there's typically some mathematical prerequisites that would be required, like studying differential equations. And then once you've learned differential equations, you'd be able to use this type of math. So a core equation in quantum physics is known as the Schrodinger equation, which is shown up here. So we'll just kind of go through it a little bit. So H of t, this is called the Hamiltonian operator, and it basically tells you the energy in a system. So over here, this is the Hamiltonian equation for a simple one-dimensional problem, like the sine x. So this is the Hamiltonian that would theoretically correspond to this simple example. And even though there's a bunch of variables here, these are actually all, this is a constant, this is a constant, and this is just a derivative, second derivative. And again, that's why you need the mathematical prerequisites to actually do this in practice, because you need to know how to take this derivative. But theoretically, you can plug this in to the Hamiltonian. So the Hamiltonian tells you the energy in the system at that time, and it's denoted by that for simple examples. So the Hamiltonian applied to the wave equation is equal to, so I, that's an imaginary number, square root of -1. H, that's the Planck's constant. And then we're taking the derivative with respect to time of this system. So although we're not going to mathematically go through everything here, this equation, Schrodinger's equation, shows you how the wave evolves over time. And that's why I have this GIF here. So let's just follow any one of these lines. So let's say that we're looking at number F here. Let's focus on that blue line. So let's say like we have a starting point, and then we use Schrodinger's equation, and then we can like plug in whatever value of t we want for time, and then we'll see how it evolves. So Schrodinger's equation theoretically describes how a wave equation evolves. That's kind of the most simple way I could explain it, is that Schrodinger's equation explains how the wave equation evolves over time. So some wave equations would be static and they wouldn't be changing, but if you had a very dynamic system, then your wave would be moving a lot. And that's the equation that would describe that. And if you studied quantum physics at the university level, on the final exam, it would be questions like this, where they would describe something to you, and then you need to learn how to take that into a differential equation, like this, or like a wave equation, and then plug it into Schrodinger's equation. And then you could learn about how that evolves with time. So moving on as well, another starting point of quantum physics that humanity also dealt with is the theories of an atom. So this is the Dalton model, which is just an atom as just like most basic, just kind of like a sphere of mass. And then moving on, J.J. Thomson, we learned about electrons and protons, positive, negative charges. So he suggested that the plum pudding model, that there was just a bunch of electrons just inside of that sphere of matter. Then moving on to the nuclear model. So this is actually the one that they teach in grade school, and they tell you, they never mention that they don't tell you the full story, but they basically, here we have electrons orbiting around the positive sphere, almost like planets orbiting. And then in 1913, 2 years later, we learned about that electrons actually have discrete levels, and this in itself is related to quantum physics. And theoretically, if I wanted this electron to move here to the next level, I'd have to give it a very specific amount of energy, which is, again, related to quantum physics and the concept of specification. But yeah, so that's kind of the next model, is the planetary model. And then finally, in 1926, Erwin Schrödinger says, no, it's actually quantum physics, and it's actually a wave equation to describe it. There's no points of the electron. The electrons exist in the cloud based on a probability distribution modeled by a wave equation. And then moving on here, so this is for a hydrogen atom, and this is the wave function that shows where the electrons are. So let's just look at any one of these. Let's look at this one on the top here. So that space is just where an electron might theoretically be. It's somewhere in that space. And that's now how we understand chemistry, is at the quantum level, that the reality is that the position is represented by the probability distribution and the wave equation. And then up here, up top, this is you can't really see it, the resolution is poor, but it's kind of amazing how even something as simple as a hydrogen atom, which is the most simple atom in chemistry, has such a complex wave equation. So you can only imagine how much more complex things get. And if you try to simulate stuff like this in a regular computer, it's almost like you solving it, because you're solving it like one thing at a time, trying to take that big square root. It's very involved. But when you're using a quantum computer, it's very natural, because like the same mathematical structure of the quantum computer is involved in the chemistry of the atom itself. Okay, moving on as well. So you may hear as well, if you're studying the mathematics of quantum computing, you might hear the term called Hilbert space. So a Hilbert space is just a mathematical space where imaginary numbers exist. So you're allowed to have I, square root of -1. And the whole rule is, whenever you're dealing with things that have I in the Hilbert space, they're only allowed to be complex conjugates, which basically means if you multiply them, so here's an example. So if Z, which could just be like represent something in the Hilbert space, is equal to 3 plus 4i, then there must be a Z bar, which is 3 minus 4i. So notice that the only difference is the plus is switched to a minus. And what happens is when you multiply them, the imaginary numbers actually cancel out, and then you end up with a real number. So the Hilbert space is just a mathematical space with imaginary numbers, where there's also complex conjugates that will cancel out. So when you multiply things, you end up with real numbers. That's the Hilbert space. As well, like it just kind of contrasts to the classical Cartesian space. So I'm sure we've all heard the terms Cartesian space, X, Y, Z. The Hilbert space is just the parallel for that for quantum computing. So in the Cartesian space, we have physical positions, like you have an X, Y, Z coordinate. Whereas in the Hilbert space, as we saw, you have a wave equation that represents all possible states. Real numbers, whereas in Hilbert space we have complex numbers. Those are kind of the main concepts, is especially that first one where you have a physical position in the Cartesian space, but in a Hilbert space, you have all possible states in a wave equation. That's the main concept. We're kind of working on the end of the presentation here. So something else that if you start learning about quantum physics, you'll hear terms that are like principles and properties, as I kind of mentioned here. So a big one is the Heisenberg uncertainty principle. You guys may have heard this one. So it's physically impossible to simultaneously know the exact position and the exact momentum of a particle, because if you measure it, it collapses, you lose information. So that's just the Heisenberg uncertainty principle, that you cannot know all that information at the same time. Another one is Pauli exclusion. So two identical fermions, this is a term from particle physics, but basically like electrons or fermions, cannot occupy the same state at the same time, which is the fundamental reason why atoms have structure and solid matter doesn't simply collapse. So it's kind of interesting, like if I push into this matter here, where like I step into matter, I'm being blocked. And there's a few different forces involved in blocking me, but one of the core ones is the Pauli exclusion principle, because the atoms in my finger can't be at the same spot as the atoms in this bench at the same time. So although it's very intuitive to us, like humans, because we always are interacting with things that we can't move through, that's just like a fundamental, that's like the proof, I suppose, is the Pauli exclusion principle. And the last one here, kind of like a more fun one, but quantum tunneling. So in quantum tunneling, in regular physics, let's say my water bottle is trying to move through this desk. It's never going to happen in classical physics, but in quantum physics, it's possible for it to essentially travel through that energy barrier. So that's just a possibility, and that's actually what happens in Josephson junctions in quantum computing hardware, where the electron is able to jump through the gap in the wire. Remember we talked about the circular wire of superconductors, and then you just cut it, and then the electron can actually pass through that cut. That's an example of quantum tunneling. So those are just some big principles and properties which you would interact with when you start learning about quantum physics. And I think my last slide here, and this is just to paint kind of a full picture for you guys. So what would you learn in a physics degree? So if you took a physics degree and explored quantum physics, these are the things you would learn. So first you'd learn about wave-particle duality, which we discussed already. Then you'd learn about the Schrodinger equation. So you would already have taken some mathematical prerequisites to be able to directly use the Schrodinger's equation. You'd learn about the Born rule, whatever. You'd learn about quantum operators. So we talked a little bit about quantum operators when we talked about the big H in the Schrodinger's equation that represents the energy, called the Hamiltonian. So you'd learn about quantum operators. Some of them allow you to find position, momentum. You'd learn about some other things, quantum tunneling. You learn about Heisenberg's uncertainty principle. You learn about angular momentum and spin, which are kind of other intrinsic properties that are quantized. And then you'd study the hydrogen atom. So we kind of looked already at the equation for the hydrogen atom. You'd probably study that and interact with the math of that. And then you talk about entanglement and some other concepts. So that's what you mostly learn in the physics degree. And after learning these things, like everyone imagines who doesn't know much about quantum physics that it's an infinitely deep subject, but it's really not. It's kind of contained. Where it becomes a lot more complicated is when quantum physics is mixed with relativistic physics, which is what Einstein was working on, which is time dilation. So if a particle is moving at close to the speed of light, the amount of time it experiences changes. So that's like a completely different topic in quantum physics. It's relativistic physics. So where quantum physics is still being explored and what most of the research is occurring is in the intersection between time dilation physics and quantum physics, and it's called quantum field theory. So that's where most of the complexity is, but in terms of just kind of a basic understanding of quantum physics, this kind of gives you the main landscape here. So yeah, I hope that's kind of all I got for you guys, so I hope that you enjoyed the presentation, and that's all. Thanks for coming.